eventually?
Something.
We make it available somewhere.
They change the way they show recording on the application.
No, but did you see I can send a like for each one specifically. Send a page, yeah. I had a YouTube channel, and sometimes when you used to go on it, it's like a big comment.
A lot of people ask. Things that they didn't talk about. Okay.
Okay, welcome everyone. This is the first CS seminar of the term. And I'm glad that you're here. At least some of you did not get that confused about my update message. The seminar was never cancelled. Unfortunately, I have Xiaoyang that offered herself to present since her speaker got ill and could not come here. Well, she will present. I'm not using her time. And I think that's actually a good opportunity for all of us that who bring people here to present, having a backup plan as an opportunity. If something happens, then we can use this time to make our time more useful and present and get feedback from our peers.
Thank you, Diogo, and thank you everyone for coming. As you probably got multiple emails, I did invite someone, but she could not make it this morning. So I'm the backup here. So instead of a shiny external speaker, today you have me. Okay, because I don't really have time to specifically prepare anything for this seminar. So this is the slides I used in April this year at an Amazon seminar. So before we start, this is not something I'm actually working on, but this is something I'm really interested in, and I read several papers about it. I think this is a good, at least an interesting research trend in the reinforcement learning area. So that's why I put this together to talk to people to see if there are possibilities or any other interesting applications related to these type of things. So today I will be talking about generating solutions to basically to explore conditional generative modeling for sequential decision making. So here by sequential decision making, I will be mainly talking about reinforcement learning. So some very brief introduction about reinforcement learning. I guess a lot of you must be very familiar with this, but bear with me a second. So reinforcement learning, as a branch of machine learning, it will study the sequential decision-making problem by interacting with the environment. If we are talking about the traditional way, so in reinforcement learning, we usually have an environment. That is the environment we are trying to play with, and our intelligent agent is trying to learn from it. And we will have an intelligent agent we are trying to train and trying to learn a good policy. So the agent can make action, and the action will go to the environment. So the environment, as a response, will give feedback. The feedback will be in the form of a reward, and the environment will usually move to the next state, which is here as t+1. So so the next state and the reward will go back to the so the agent can learn from these whole interactions. So mathematically, this problem can be described as a discounted Markov decision process. So we will have a 0, that is the initial distribution of the states, and we have S, that is the states, showing the different attributes of the environment. And we will have A, that is action space, showing all the possible actions for the agent. And we have R, that is our reward, and we have P, that is the transition probability. Say the environment will transit from ST to ST+1 with some probability. But sometimes it will be deterministic, sometimes it's not. So the whole story about reinforcement learning is we're trying to learn a policy that can maximize the return. So return is defined here. So return will be return will be the sum of the discounted reward. Here we put a discount factor to avoid, say, if the time horizon is really long, to avoid like huge numbers. And here is how we define a trajectory. Because in reinforcement learning, an agent is interacting with the environment. So the trajectory will be the current state, what action we did, and what is the reward. And this will goes on and on with this time t. So this is how we define trajectory. So the whole idea of reinforcement learning is, given this environment, and we're trying to learn an agent which can perform a good policy. So a policy means, given a state, we know what action to do to get a high reward, to maximize this return. Okay, so this is just a brief introduction about reinforcement learning. And next thing I want to talk about is called temporal difference learning. So you will usually see it as a TD method. So TD method is trying to optimize the policy the agent can perform. But the way to update it is using this second equation. So we are assuming that at current state, that is S, if we do the best action A, then it will be equal to, if we actually perform this action at this state, this will be the reward we get, and plus some discounted future state action value. So this is the whole idea behind the TD learning. So here, the D will be a data set of transitions or a data set of trajectories. So as you can see from here, so TD learning is trying to learn some information from the data set of transitions using a specific way to update our policy. So, but here you can see there is a max function. This will only work if the action space is discrete. So imagine the action space is continuous, meaning, say, we can perform any action between 0 to 1, then the max function cannot be performed correctly. So if the action space is continuous, then we will replace by a trainable policy. So a policy will tell us, okay, what is the best action we can do here? And so we can apply the same idea with TD learning. So TD learning, and this way we update the policy, we call it bootstrapping. And because it's learning from the data set, and here we are assumed that for the next state, we will perform the next best action that will give us the maximum Q value. It doesn't have to be the same policy we are using when we are interacting with the environment. So this is what we call off policy. Meaning we are trying to learn from a policy that does not necessarily to be the policy we are performing. So we're learning from, let's say we are learning from someone else's experience. So that is what we call off policy. So bootstrapping and off policy, we will talk about these in a later slide. But yeah, these are kind of the difficult parts of doing TD and reinforcement learning. Okay, then we can talk about what is offline RL. So in my first slide about a brief introduction on reinforcement learning, we said that reinforcement learning is all about having an agent interacting with the environment. But of course, we can perform it in an offline setup. So this is the one on the left, that is the traditional way, that is online reinforcement learning. We have an agent, the agent interacts with the environment, get feedback, and update itself. So in the middle is what we talked about off-policy reinforcement learning. Off-policy doesn't mean offline. Off-policy just means, okay, we have an agent, and the agent will interact with the environment. And so it will get some data, and the data goes to a buffer. And so, as you can imagine, this buffer can have trajectories that are collected by different policies, but they all goes into the same buffer. And when we try to update our policy, we will use the data in this buffer. That is what I talked about. The reinforcement learning agent doesn't need to learn from the trajectories that are generated by its current policy. It can learn from data generated by different policies. And if we update our agent in this way, then it will be off-policy reinforcement learning. Then the figure on the right, that shows what is offline reinforcement learning. So offline basically means we removed the online interaction part when we train our agent. But we still need an agent. We still need it to interact with the environment to collect some data. But once we have the data, it all goes into a buffer, or we can say it all goes into a data set. And what we do is we try to learn a good policy from just having that data set without any access to the environment itself. So it will be like we have a data set and we don't have the environment, but we still try to learn a good policy, and at the end we will need to deploy that policy to that environment. As you can imagine, without online interaction and online instant feedback, this is going to be much more difficult. So the idea of offline reinforcement learning is given a fixed data set of transitions collected by unknown behavior policy. So we don't even know what is the agent that has collected this data set. Say, someone might give me a data set, say, okay, this is a robot playing with something in a room. I don't know what is the predefined policy for that robot, but what I can do is I can try to look at that data set and learn probably a better policy from that. So the first thing is we don't know the behavior policy that is used to collect this offline data set. The second thing is, it removes the ability for the agent to explore because we don't have access to the environment anymore. So, but the reason why we are thinking about offline reinforcement learning is, in a lot of cases, we cannot always interact with that environment. It's either very expensive or not safe at all. But to replace this, we can also develop what we call a digital twin. But developing an accurate digital twin is also a challenging task. And as we can imagine, the digital twin must be in some way slightly different from the real environment. Then we are introducing another problem that is the sim to real gap. So this is why we need to think about offline reinforcement learning. The last thing is, because currently we do have a lot of different data sets for different tasks. If we can make better use of these already existing data set and to do data-driven reinforcement learning without heavy interactions, then we could probably be more efficient in this area. So this is the idea of offline reinforcement learning. And the challenges are, first, we're trying to find a good policy. And we're usually trying to find a better policy comparing with the data set we have. So we're learning from data, but we're trying to do better than that. Another thing is, for offline reinforcement learning, sometimes the learning algorithm will be required to stitch in different parts of good behaviors from different trajectories. Like in your data set, you might have several different trajectories. The first one might be really good at the first part of the task, while the second one might be really good at the last part of the task. So the learning algorithm is usually required to have the ability to find these good parts and stitching them together to make a better policy. That is usually how people think about it when they're talking about learning a better policy from that. Yeah, and if we can do a really good function approximation, like we can really learn what is the good, what is the policy that is used in collecting this data set, things like this. It might help solve other tasks. So it will generalize better. But as the challenge of learning from any kind of data set, we are facing the problem of overfitting to that data set and remove the ability to explore. So this figure is a nice visualization of what usually happens if you are trying to learn from an offline data set. So you will expect to learn some trajectory, and at the beginning it might follow what you are expecting, but then at some point it will diverge, and at the end you will have a different policy.
Sorry, it's my misunderstanding, but as you said, reinforcement learning is about learning to maximize reward, cumulative reward. And here you're talking about copying behavior. Sure, you can restructure the reward function to be about copying behavior, but otherwise it seems like there's a bit of a shift towards more imitation-like learning you're thinking about.
Yes, so yes, that's a very good point. So a big part of doing offline reinforcement learning is first to start with trying to replicate what happens in a data set. But the next thing we want to do is we want to have a trajectory that can achieve higher reward comparing to what we have in the data set. Yeah, but not always possible. Yeah, so for this slide, what I want to talk about is what we call the W triad. So, okay, so in any type of reinforcement learning, if we are applying deep learning, say neural networks, we are doing function approximation. And when we talk about TD, we say, okay, TD is about doing bootstrapping. And because we're trying to learn from a data set, and we don't know what is the policy that collected that data set, so essentially we're doing off-policy learning. So there is a theory in reinforcement learning that says that if these three things happens at the same time, then the learning will be extremely difficult, as we can imagine. Yeah, so if we want to move away from like having these three things at the same time, so we want to move away from TD learning, we want to move away from bootstrapping, then currently there are, I think, two different ideas. The first is to do sequence modeling with transformers, because transformers are very good at that. And the thing we are trying to learn in reinforcement learning is essentially a good trajectory or a good policy that will give us a very high reward. So the first idea is people are trying to use sequence modeling methods like transformers to model offline reinforcement learning. The second thing that I'm more interested in is how to do conditional generative modeling. Okay, I will talk about both of these ideas. So the first is how to do sequence modeling with transformers. Yeah, it's based on this paper. It's from 2 years ago and from the UC Berkeley group. Yeah, so this idea, I call it like transformer-based approaches. Essentially, it's a shift in the reinforcement learning paradigm. Say, if we can model the joint distribution of the sequence, say states, actions, reward, can we use it as a replacement for the traditional reinforcement learning? Like, we just learn the joint distribution of all the states we want, all the actions we want, and all the rewards we want, instead of learning it step by step. So we learn the whole trajectory instead of learning every single step. So the idea of decision transformer is to use existing language model modeling framework with minimal changes. Hopefully, it can learn a good trajectory, and it will be model-free. By model-free, we mean we don't have any idea of what is the transition probability of our environment. So we're just learning from data. We're not trying to simulate that environment, and it will be offline because it can learn from an offline data set. Let's see how they do it. So in reinforcement learning, what we want is we have an agent, we have a state, and the agent does some action, it will move to the next state, and we get some reward. So this kind of trajectory, or this kind of sequence, they are trying to do this by using a causal transformer. So the idea is, okay, I can have a state at t-1, and I can, hopefully my transformer will give me the action I should do at t-1. And I will take this action as input. So we have a longer sequence as input, and hopefully it will give me the next action I should do. And it will work like this. But the core part here will be a causal transformer. So it's like a GPT architecture. It's an autoregressive model to predict actions using the previously predicted action from the same model. So as you can see, it's quite straightforward. The whole idea of doing decision transformer is just imagine a trajectory as a sentence or something, and you're trying to predict what is the next word, like GPT. Yeah, but they did make some changes. First, if you look at here, we already talked about reward, and we are trying to maximize the reward when we are doing reinforcement learning. But here, they are not just using reward. They are trying to use what they call reward to go. Reward to go means from the current time point. So here, from time t, what are the future reward I can get from this trajectory? So instead of giving the current reward, because current reward really tells a little information about the environment. But if we give the reward to go, say the summation of all the future reward as an input, so we're trying to tell this model that this is the reward I want to get at the end. So please try to make that happen by giving me the correct action. So reward to go in this case will be much more useful comparing to the current reward. The second thing is the discount factor here is removed, but as the author said, this is just a design choice. You can keep it and try to see what happens. But by using this sequence modeling method, we removed the need for doing bootstrapping. We're not just learning from the current step and try to find the difference between the current step and next step. But here we are treating the state action reward as a whole trajectory and trying to do sequence modeling. So I think this is the core idea of this decision transformer. So first, we will represent the trajectory using reward to go rather than the reward at the current time step. Then we will have a sequence, and imagine it will have k time steps, and they will be transformed into tokens because we have a reward to go, state, and action. So for a sequence with length k, we will have 3 times k tokens here. And another important thing that makes transformer work is it uses positional embedding. So here it will also use positional embedding, and this embedding will be added to each token. So basically they just slightly modified the way we represent the trajectories in reinforcement learning, apply a transformer model, and hopefully it works. And from their results, it does work. So yeah, but this is all for training. So for training.
Sorry, just a quick question. So for the decision transformers, the set of actions that you are following to get you to the reward that you're after, are you considering that that's to be fixed set of actions, or like because it can be like in a case that when you are doing an activity that is just comprised of multiple steps, some people might go different paths, but it will still take you to the same state. So can it like cover multiple paths that they take you to one state, or is it like a fixed set of actions?
Yeah, I think so, because it's learning from the offline data set. So the actions will just be the output of the model, and they're doing it in a supervised.
What if it's offline? That means it depends on how much exploration has been happening in terms of actions in the one that you have.
Yes.
So if different paths are not covered, then that means you will not be able to recover.
Yes, because we don't have any information about the environment except for the data set.
Yeah.
Yeah.
But there are infinite number of possibilities which you can't cover basically.
Yeah. So this is actually the next thing I want to talk about. So in training, it's all fine, but in testing, how can we find the reward to go? How can we find the desired output from this trajectory? And that is heavily dependent on that.
Can't you make a distribution on the infinite number of possibilities?
I think we are trying to model the distribution of the high reward, or the distribution of reward that we can actually get from this data set.
That's related, yeah.
Yeah.
Makes sense.
So in a decision transformer, do we also predict the reward? Do we also take the reward as the output?
So in the training stage, no. In the training stage, we're just trying to take action as the output. But it's an autoregressive model.
But how the reward is reflected in the training process?
In the training, so the reward is put as reward to go as part of the trajectory. So at step 1, I expect at the end I can get 100 as reward. So at step 1, it will be 100 current state. I don't have action yet, so the model will give me action, and for the next step, I will take that action and a new reward to go to the
so the reward actually is an input to the.
Yes.
Okay.
So we're trying to predict the action.
Okay.
Okay. Yeah. So as I just said, so in training it's all fine. In testing it will be a bit tricky, but the authors showed in their paper that because they're testing on some graph problems and other games. For games, sometimes you can get an idea of what is the highest score you can get, but it's not always feasible with other applications. Okay. Yeah, so these are some, I would say some nice features of their method. So first, in this experiment, they showed that the decision transformer can stitch some good behaviors. So this is a toy example showing how to solve the shortest path problem from just random walk data. And as you can see, there are some, so in the middle, there are some samples from the training set. They are good in some sense or in some steps, but at the end, the optimal solution will be to stitch this orange one and this blue one. So it does have some ability to stitch good behaviors. And so it will be better than simply performing behavior cloning. Yeah, so this is all I want to talk about the decision transformer. But basically at the same time when this paper has been released, there's another paper, also from UK Berkeley team, and one of the authors is Sergey Levin. I don't remember the title of that paper. I can probably find it. Yes, so yes, so the one I just talked about is called a decision transformer. But this is also one paper that used a very similar idea, published roughly at the same time, and it's called offline reinforcement learning as one big one big sequence modeling problem. And the model here is what they call a trajectory transformer. Because it's a while ago, I don't really remember what's the key difference between these two papers, but like really similar ideas. Applying a transformer to model the sequence rather than just trying to generate the next great action. So if you're interested, I will recommend to read both of the papers. One is decision transformer, another is offline reinforcement learning as one big sequence modeling problem. Okay, let's go back here. Yes, so then we can come to the second idea, that is conditional generative modeling. So, yes, so in these types of work, they apply a powerful generative model that is a diffusion model. So I will briefly talk about the denoising diffusion probabilistic model that is a very commonly used one recent days. It's called DDPM. Briefly, the idea is, okay, so we start from an image at the right-hand side. In the forward process, we will try to add a little bit noise on every step, add noise to that image. So it will become more and more blur, and with noise, and it will be difficult to identify what's in there. So at the end, we will have something that is like sampled from a Gaussian noise. And in the reverse, in the reverse process, we will just try to predict that noise and subtract the noise from each of the steps. And at the end, we can get a clean image. So this is a Markov chain. So this is a very rough idea of the diffusion model. But people are also using diffusion model to do other types of data generation, like text to image. So it will be all like conditional modeling. Yes, so the main idea of diffusion model is try to learn the data distribution from the given data set. Like if we are given a bunch of natural images and to train a diffusion model on that is actually trying to learn the data distribution of that set. Yeah, so from X0, that is the clean image we have, we will then go to, at the end we will have XT. It's basically a sample from isotropic Gaussian, and if the T is long enough, so the forward process will be adding noise, and the reverse process will be denoising. Yeah, and the way a diffusion model works very well is someone has proposed a simplified loss, so it makes it easier to train. Anyway, I won't talk too much about this. Yeah, so these are the algorithms that we use to train a diffusion model. So as you can see, a good feature is in the forward process. So in the training stage, we can basically sample T at any arbitrary time step. we don't need to add noise from step 1 until step t. We can just sample any random step, and we know how much noise should be added to there. But for the reverse process, it needs to be done step by step. So that is called sampling. So if you look at algorithm 2, in the sampling stage, we need to start from some random noise, and we denoise it step by step. And as you can imagine, it can take quite a long time, because in diffusion model, we usually talk about hundreds, even thousands of diffusion steps. So that is the feature of diffusion model. But since it's a very powerful generative model, then people start to think about, can we formulate the sequential decision making of reinforcement learning as a conditional generative modeling problem? Again, we are trying to deal with the whole trajectory rather than deal with single steps. But here, we want to use a different generative modeling, that is diffusion or conditional generative modeling. Yes, so there is a paper last year. I don't like the title. It's called "Is Conditional Generative Modeling All You Need for Decision Making?" Yeah, that's the title.
Why did you like the title?
Because I don't like people say something is all you need.
Okay. It's gonna be
I
cheesy.
mean, all you need is a big word.
It's not claiming that it is, it's just asking if it's...
It's just using the meme. It's just saying, is attention all you need? Like attention is just repeating that.
I know.
that one got
That
the,
one.
That one got the hype, so they just
Yeah.
following the same path.
That's it. But it's 2022.
I have one comment. It's about the number of time steps to generate real good images. Right now, actually, it can work for like 50 or maybe 10 to 50. It can already generate very high quality images. We really don't need to go to like 100. Yeah, so 10 or 50 actually, it's like
I would imagine.
maybe like 30 seconds probably. Yeah.
Yeah, but I guess it also depends on the task. Say, if we are just trying to generate an image that follows the same distribution.
Actually, I'm talking about the task for text-to-image generation.
Text-to-image.
Using stable diffusion.
Stable diffusion.
So actually, 10 time steps already give really good high-quality images.
Yeah. I only tried stable diffusion once, but my impression is it takes a lot of memory to even generate.
If you that's no memory, that's not the time.
I know you're talking about time step, but it's just a side comment.
Okay.
It takes a lot of memory.
So we'll take you back a little bit to decision transformer. How it could perform if it goes to complicated time series of trajectories, like complicated trajectories or complicated sequence of trajectories.
So are you talking about?
Did you test how it could perform? Because we can speak about simple kind of trajectories, but if we discuss like complicated time sequence of trajectories.
Yes, I guess there are several things they did. First is actually in the decision transformer, the sequence is not too long. It's usually, I think in their paper, it's 8 steps or something, so it's not too long. So it's avoid some of the complexity. The second thing is, I guess decision transformer will only work for certain cases. There are cases that the performance is not really well.
Maybe you can do embedding, vector embedding. For example, you have really complex data. You do some kind of embedding by using a neural network, right? Then it output is a vector, and then you take the vector to be input to the decision transformer, right? That's one way you can.
I think as transformer solve the drawbacks of neural networks, and we shouldn't go back to that area. I think reconnect neural network, neural learning. Sorry.
Just my personal view, I won't say transformers are solving the drawbacks of neural networks. It's just a slightly different. It's just a slightly different.
Reconnect neural networks.
Yeah, I guess it's.
Neural learning. Sorry.
Yeah, I guess it's just a slightly different structure to enhance its ability on long sequence modeling. That's how I understand it, using the attention mechanism and other tricks they put. Okay, where were we? Yes, so this is the second idea. People are trying to think about, can we formulate this sequential decision-making problem just as a conditional generative modeling problem? This paper is called a diffuser. Use a guided diffusion model for offline RL. Again, it's model-free because we don't have any information about the environment. But one good thing about this is, since we're talking about conditional generative modeling, the condition doesn't have to be reward. We can also put things like, if there are any constraints on the trajectories we want, we can put that as a condition. And if there are certain skills we want, then we can put it as a condition. So by doing this conditional generative modeling, we're like opening more opportunities, not just focusing on maximizing the reward. Yeah, and this paper is called Conditional Generative Modeling, All You Need. Okay, so this is their algorithm. So basically, they will have they call labeled trajectories. That is the information we get from the data set. But here, we can have, say, reward. We can also have constraints, and we can have skills. These can all come along with the data set. And so we can also have different goals. Like, if we condition on different things, then we can say we can maximize the reward. We can try to make our agent satisfy certain constraints, or we can make them to combine different skills. So this will be, I would say, more flexible comparing to just trying to maximize the reward. Yeah, and what we want to generate is we want to generate portions of trajectories, or just say we want to generate a trajectory. So we're not learning a policy, but we are directly generating the whole thing, just like if we use diffusion model to generate an image. So we're trying to generate the whole thing at the same time. But we can put conditions. So conditions can be the return, that is the reward under the trajectory, or some constraint, or some skills that has been demonstrated in that trajectory. So it will be slightly more open area. Yeah. So what did they do is, first is how to model trajectories. Here, it also requires some special design. Although they are talking about modeling trajectory, actually what they model is just the sequence of states. Because as in a lot of problems, actions are discrete, and actions can really change from step to step. So it's not easy to model that. But states, in some sense, are more continuous or more connected to each other. Say, if you are playing with a robot, the robot will not jump from one side of the room to the other side of the room in one step. But in two successive steps, you can make very different actions. So that's why they only model states here, but without actions. Then, if they can generate a sequence of states, the next question is, how can we get actions? Actually, getting action is the simple part, because we have the data set. We know if we are transforming from ST to ST+1, what is the action has been taken. So they're just training a supervised model to predict actions if we know the current state and the next state. But in their diffusion model, they are just modeling the states without any actions to avoid the confusion to that model. Yeah, so this they call inverse model. This can be trained very easy from the data set using supervised learning. Yeah, then we can talk about the guided part. So in here, we just look at, okay, this is how they model their trajectory, and this is what they want to generate from the diffusion model. But we can put conditions. So in this paper, what they did is use what they call classifier-free guidance. So the guidance can just be injected into this loss function, so we can easily train that. So the guidance can be reward, can be constraints, can be skills, like we just said. But we just need. But first, it will be a function of the trajectory, and second, they can just be easily put in this equation. And if we are looking at neural networks, then it will just be a different hat. We just put it in there and to train the whole thing end to end. Yeah. So about put constraints and scales, they are the same. So assume we have a data set demonstrating different constraints. So then we use this guidance function. That is a function of the trajectory. So we sample from this data set with different conditions, and we train this loss function. So we can have different. So the point of this equation is we can have multiple constraints put in the same time. So I equals 1 to n. So we can have multiple scales, multiple constraints, all from the same data set, as long as we model them separately using different guidance. Yeah. So, but here the assumption is the condition or the constraint is independent given the trajectories. So because they're independent, we can do a simple summation. But if they're dependent on each other, then we cannot do this. Okay, so this is an interesting result, I think, from their paper. So assuming this 2D plane is their environment, and for the one with the blue dots here, the constraint is x and y should be outside that circle. So as you can see, their generated states are basically all outside of that circle. And you can also put constraints like inside that circle. So that's the yellow results. And you can put things like they need to be between the bigger circle and the smaller circle. So that is the third results. So this is a toy example to show that adding constraints to this generation process actually works really well. At least for this simple case. Well, yeah, because this is my previous slides, I put work in progress. But these are not the things I'm working on. So we used to be looking at graph-based diffusion models. So people are trying to use graph diffusion models to solve combinatorial optimization problems, basically just to generate the solution. But yeah, it's a bit tricky and difficult to evaluate. But currently what I'm doing using diffusion model is, say if we give the model a big enough data set, it can learn a very good prior. And if we want to generate anything from that distribution, we can use it as a prior and inject the information we want to push the generation to the direction we want. So this is what we are doing using a diffusion model, and to achieve, we are trying to achieve a good sensor fusion results. And that's a different topic. It's not offline RL. It's more about sensor fusion. Yeah. So the summary is, like in my own opinion, I think reinforcement learning is moving really fast from online to offline, simply because we have a lot of data. Online interaction is expensive and sometimes not feasible. So we want to make good use of that data set. Yeah, and there are two streams of research when people talk about doing sequence modeling on reinforcement learning. So first is transformer-based, because that's like the most famous model for sequence modeling. The second thing is treating RL as a conditional generative modeling problem. And the existing work is using diffusion models. Although these are from, I would say, at least half a year ago. I don't know if there are new works on this area. But I think conditional generative modeling really gives us the flexibility to inject not just the reward we want, but also like how the trajectory we want it to look like, any constraints or any other things we can put as conditions.
For offline, how would you validate them?
Yeah, so for validation, people usually deploy the learned policy to a real environment. But by real, I mean a simulated environment sometimes to try to collect results. Yeah. Otherwise, we cannot evaluate.
Yeah.
That's all.
Thanks.
Sorry, on just your last point. So then, when you again face the same problem as simulation into real world, why don't you go again with like do everything, exploration, the whole thing in the simulation environment, and then?
Yes. So sim to real is a big problem in any kind of, if we want to do real deployment. Yes. So we need to. Usually, people will allow very little rounds of interaction and exploration under safety constraints to help to refine that policy. But there is a work about using reinforcement learning to control a token mark. It's called token mark. Yeah. so basically control some very, very dangerous devices, I would say. Yeah, and they can do that because they have a very accurate digital twin. So they don't need to do any tuning on the real environment. They just have a good enough digital twin and they can happen. But that is expensive.
That's right. I totally agree with you that online reinforcement learning is not the way to go. It's just not.
Yeah, we can make a use of big data set. We can do things in parallel.
Yeah.
Okay, so in your opinion, this last one, this diffusion, what's the name? The last, the second approach. Yeah. So in your opinion, what's the let's say drawback? Inherent any drawback when this approach? I mean,
I don't know.
can inherent any space that or any room that we can further improve?
I think first, because you are working with diffusion models,
Yes.
so it highly depends on the data set we're giving it. And second is, how do we want to put our constraints? Because here, we cannot learn, they haven't explored the possibility to learn constraints from the data set. So the constraints they put here is basically some outside information or outside knowledge. They say, okay, I want my trajectory has a high reward, but maybe there's something to explore there. I would say, yeah, the model is trying to learn the data distribution, and if we put conditions to try to push the generative trajectory to the direction we want.
Yeah, it's kind of already standard. I mean, everyone knows that.
Yes.
Because this text-to-image generation is a very good example.
Yes.
It's a conditional generative model. Yes, actually, it's like a common standard. Also, this classifier-free guidance is also kind of standard technique.
Yeah, but the challenge here is how to have a policy that performs better than the data set by putting the right condition and make the model learn in the right way.
Another question actually, because recently, I'm not trying to supervise a few students, right, on the master's project, and some students want to do deep learning stuff, deep learning, and then their laptop or their computer cannot handle this deep learning, heavy deep learning models. For example, diffusion model is very heavy. So actually, I wonder if our university has any GPU facilities that students can use.
David is the module lead.
And then we'll be able to answer your question based on the response I get. I haven't had time to do it, and I was only sent the form yesterday, so I will. The Google Cloud credits I'm looking into, and there was a second one.
You mean Google Colab?
No, Cloud.
Well, I don't think you can use Google Cloud credits for Google Colab. But Google Colab is what they need in terms of the GPU stuff. Yeah. But I don't think you can use the credit for Colab.
I will fill out the form this afternoon and see what response we get from Google.
Because many students are looking forward to that.
Yeah, right.
Because Matt promised there will be something.
I mean, it's on campus somewhere. The hardware's like here, and it's been here since April last year. So I don't know why they haven't plugged it in, but there's the research computing infrastructure, ISCA, which should be
hidden with the robots from Xiaoyang.
I think robots are more tangible than the clusters.
But there's GPUs left over from the computer vision group, I think. I'm looking at you because I thought you had that.
I gave one to her. I don't know if there are others.
I don't know.
But it was not GPUs, right? There was one.
That was only one.
Singular.
That was a single.
I thought there was GPU clusters on a couple of recent grants.
Maybe this is a discussion for another time. That's all.
Good question.
That's a really important discussion. Like to run a diffusion model, it's not just about GPU. We need GPU with a large memory.
Yeah.
Right. Yeah.
Well, I have a question about how can we fix the gap between simulation environment and the real world?
The answer is people don't know. So it depends on different situations. Like the case I talked about, Tokamak, they built a very accurate simulator. And I would say the successful cases are basically all doing that. The other thing is you can try to learn because Because for the difference between simulation and the real, there must be some difference in the distribution of their transition probability or distribution of other things. If you can try to learn this difference of distribution and try to transfer your model in that way, then yeah, it's also another possibility.
I mean, if you put a joint distribution on this trajectories, I mean, you could quantify the uncertainty. I mean, do people use this uncertainty in predicting the next action, for instance?
Specifically in reinforcement learning, in the paper I have read, people don't always do that.
Yeah, I don't think so it's that easy because I think it will make it more expensive. But it's possible.
Yeah, especially in online reinforcement learning, it's not really feasible because it's learning by trial and error. If you try enough times, then yeah, you can basically cover the common cases.
Another question. So this is two approaches. This is either transformer-based or it's diffusion-based. Do they really perform well, perform better than the classical reinforcement learning approach?
Well, in offline reinforcement learning, yes, because
they really perform better than the.
Well, but I would say they're slightly different paradigms because online is you have access to the environment, you can get feedback. So in theory, it will be better, right? But here we are trying to learn from the offline data.
Yeah.
Yeah. So what we want is a satisfactory performance compared to other. Don't know who
Sorry, go ahead.
Yeah, please.
What problems are you applying these methods to, or are you?
Yeah, so this is also a question I'm thinking about. Currently, I am using diffusion, but it's for sensor fusion. It's not for this type of reinforcement learning. My previous work on reinforcement learning is based on optimizing 5G and 6G networks. Yeah.
I'm going back to the question that was asked at the beginning. I'm really interested in where those conditions are coming from. I just wanted to check, did I understood it right? At the moment, we just don't know.
So a lot of reinforcement learning test environment is based on games. For games, people roughly know. Or say, if they build a simulation environment for a robot, they roughly know what do they want to do.
Then they come from the application domain,
yes,
so to speak.
Yes.
Yeah.
But I do think finding the good constraint or basically finding the good results we want to get from the data set is actually a big part of it. Because there are not much modification we can do, either on transformer or on diffusion. But how can we condition it on the thing we want?
So the transformer-guided reinforcement learning, so does the embedding generated by the encoder of the transformer mean anything? So if we have multiple sequence, like reward, action, state sequence, and we take those embeddings, do some like average, does it mean more generalize the situation like states? That doesn't mean anything. So has the authors investigate that?
No, I would say just imagine them as sentences, and that's what they're trying to do. Just to generate your answer one by one.
Okay. But I'm thinking like because that's inspired by GPT model, so GPT has multiple decoders, so it just uses the embedding as the input. So always the embedding and embedding. So
yes, just
I think like so if like we have like multiple sequences and we recorded those embeddings generated by the transformer, and do you think like if we take some such as average and they represented some states we never seen, so it's like outside the offline data set, outside the buffer.
Yeah, but the thing is, from the offline data set, if you are combining different trajectories, you don't know because different trajectories are maybe start from different states, and yeah, they are doing different actions to get to the middle states. So it's not really to combine them.
Very nice presentation.
Thank you. It's supposed to be an external speaker, but anyway.
I like the idea of having internal speakers as well, because I mean, not everybody knows what the other people do. So I wouldn't say you were a replacement. It was really a very nice talk and was very useful.
Yep.
So I'm actually really happy to share.
Yeah.
Thank you very much.
Please, let's finish the biscuit, otherwise next week we have fewer and fewer.
Alright, let's eat it all.
I'll do my share.
Similarly match. I put all the discussion that we did. Bullet points,
That's Friday, October 19th. Thank you anyway. Remembering going down.
Make it happen. I was thinking like maybe I should ask you to do it in latex. Mark down is good enough.
Friday, something like that.
Based on this template. So I didn't even offer a template. I thought of doing that or like, but no, it just chose to do markdown. I mean, markdown is what it does basically. I just clicked like copy, and then the output I got was markdown. And, like that was its choice. I didn't even like did the GPS handling of like sites and journey, very flowery language. I can't believe it.